In this video, we'll see a proof of Theorem 4.4, otherwise known as Whitney's inequalities, which says that for every graph G, the vertex connectivity is at most the edge connectivity, which is at most the minimum degree of the graph. So let's prove this. Notice that we've already seen, in an earlier video, we've already seen that the edge connectivity is bounded above by the minimum degree. Remember, the idea with this was to take a vertex of minimum degree and remove all of the edges that are incident with it. That was an edge cut and establishes this upper bound on the edge connectivity. And so it remains to be seen the, I'll just write it, so we'll see that the connectivity, the vertex connectivity of G is at most the edge connectivity of G. So let's deal with some fringe cases first. Let G be a graph of order n. And so what I mean by fringe cases is, okay, well, what if G is disconnected? So if G is disconnected, well, then the inequality holds, because then the connectivity of G is equal to 0, and the edge connectivity of G is also equal to 0. So it takes care of that. And the other fringe case would be if G is complete. And in both of these cases, the inequality holds, because then the vertex connectivity of G would be n minus 1, right? We need to take away n minus 1 from the complete graph of order n in order to make it a trivial graph. And that would also be equal. We saw in a previous video that the edge connectivity of a complete graph was n minus 1. So we may assume that G, any other fringe cases I wanted to deal with here? Yeah, we assume that G is connected and not complete. I think those are the ones I wanted to get out of the way. Okay, so, right, we want to establish this bound, so let's give ourselves an edge cut, and we'll find a set of vertices that's smaller than the cardinality of the edge cut that will disconnect the graph. So let X be an edge cut with cardinality equal to, so in particular, we'll let it be a minimum edge cut. And notice that this will be less than or equal to n minus 2, since G is not complete. Right? The edge connectivity is n minus 1 if and only if G is complete. So G minus X is disconnected, and since this is an edge cut, it consists of two components. Disconnected, and has two components. Say our two components are G1 and G2. So we'll say G1 has order k and G2 has order n minus k. So this may seem similar to when we proved that the edge connectivity of a complete graph is n minus 1, right? We start off in a similar thing, and actually we'll see that same argument play out to eliminate another edge case, or a fringe case. Order n minus k, right? So the deal is here we have G1, we have G2, and then we have some edges going between these, and the number of edges here is the cardinality of X, which is my edge connectivity. So we have two cases here that we want to consider. Case 1, I think I can type this one out. So case 1. So what if every single edge of G1 is adjacent to every vertex of G1 is adjacent to every vertex of G2? That's case 1. Every vertex of G1 is adjacent to every vertex of G2. Now this was exactly the case when we proved the edge connectivity of the complete graph. So in this case, there are, well, I'll just say in this case, the edge cut has cardinality equal to, right, this had order k, this had order n minus k, equal to k times n minus k. And right, just like we did when we proved the cardinality of or when we looked at the edge connectivity of the complete graph, we showed that this was at least n minus 1. However, we're not concerned with this, right? We know that we're just dealing with a non-complete graph, and so the edge connectivity is at most n minus 2, and so this contradicts the edge connectivity of G being less than or equal to n minus 2. So this case is the same argument for complete graphs, and we don't need to consider that. We've already dealt with that fringe case. So case 2, well, in this case, what's the opposite, the negation of the statement above? Well, that would be that there exists a vertex U in G1 that is not adjacent to vertex V in G2. So there's at least one non-edge between G1 and G2. So let me redraw our situation here. So here's G1, and here's G2. Here's my vertex U in here, here's my vertex V here, and I'm assuming these are not an edge, or this is not an edge between them. They're not adjacent. So U could be adjacent to other vertices over here, right? Might have some other vertices over here. V could be adjacent to some other vertices over here. Things like that can happen, but we know there's at least one non-edge. So what we're going to do here is we're going to define a set U that will turn out to be a set U of vertices that will turn out to be a vertex cut. How are we going to define these? Well, we're going to use these two vertices U and V. So I don't want to say bye. So let E be in this edge cut. Remember, this edge cut is all these edges between G1 and G2. So suppose I have an edge in my edge cut. I'm going to select one of its incident vertices to put into U. So I'll say if E is incident with little u, say E is U V prime for some V prime in G2. So that would look like this. That would be one of these vertices that it's incident with. We would call this V prime. Then put V prime in U. So any edge that's incident with U, I'll put the other vertex V prime into my big set U. And then if E is not incident with U, say E equals U prime for some, so this would be the case, like here I have U prime and V prime, something like that over there. So U prime, V prime, then put U prime in U. So for every edge, I loop through all of the edges in this edge cut, and I perform this operation. And so what should be clear is that for every edge E in the vertex cut, one of its incident vertices is in U. So that establishes that the cardinality of the vertex set U is at most the cardinality of the edge set, right? For every edge, I put just one vertex in there. Okay, and right, so that's cool. Now I want you to notice something. U and V are not in the vertex set, are not in U. So I'll say, but U and V are not in U. These are not removed, right? By the way, by this procedure, I would never remove U and I would never remove V because U and V aren't adjacent. So these guys aren't in this vertex set, U. And so when I remove U, so in G minus U, U and V, I can say there is no UV path. No UV path. That is G minus U is disconnected. So how do I know that? So I don't remove U and V, they're still in G minus U. And then I've removed, by removing one of each of the incident vertices of each one of these edges, I've removed all these edges. And so I would still have at least these two components, G1 and G2. U is in G1, V is in G2, and so there'd be no way to get a path from U to V in G minus U. So G minus U is disconnected. U is a vertex cut. Hence, the vertex connectivity of G is at most the order of U, or the cardinality of U. Hence, we have that the connectivity of G is at most U, which is at most X, which is my edge connectivity of the graph G. And so that's what we wanted to prove. And that's what we wanted. Okay, so yeah, just to kind of say this again, what did we just prove? We just proved that the edge connectivity is always greater than or equal to the vertex connectivity. And in doing so, we've also established that the vertex connectivity is at most the minimum degree as well, although that could have been made with an observation. So this will be useful. I'll mention, yeah, this really quick follows from that upper bound on the edge connectivity. It establishes an upper bound on the vertex connectivity of the graph. So this theorem's not too bad. I'm going to let you look through this on your own, but this term here, I'll say a few things about this, is the average degree of the graph, right? Remember that the sum of the degrees is 2m. And so if I divide this by n, this would be the average degree. Of the graph. In particular, yeah, I'm basically giving you a proof sketch here. In particular, the minimum degree of G is at most the average degree of G. And so remember that the vertex connectivity of the graph is at most the minimum degree. And so And since it has to be an integer, we can go ahead and take the floor of this average degree. And that establishes this one. So this gives us an upper bound on the connectivity of a graph in terms of its order and size. Okay, I'm going to be finished with this video. I'll see you next time.